We will now finish up our series of lectures dealing with the measurement process. In the previous 2 lectures of this series, we've covered the following steps involved in the measurement process. Now there's one more step to the process, and we'll take care of that in this lecture. The last step is the calculation of the results, adjusting for any scaling or dilutions that happened in the processing and sampling done earlier. Yes, we have finally completed a good quantitative measurement. But even if we find all the systematic error, we're not done. We still need to assess and quantify the precision of the measurements. You see, we all know that there's still a gremlin present in even the most accurate of measurements: random error. Random error is always present in every measurement, right? Now, here's a very important point to remember that is a result of random error. In every quantitative measurement, there is going to be a point where we have to guess or estimate that last digit of the measurement. For example, let's use a ruler to measure an inchworm. Okay, I know it sounds stupid based on the name of the critter, but let's do it anyway. First, you can see that I had a tough time getting that bad boy to lay flat. Well, okay, we'll live with that. Now, I'm sure that the inchworm is at least 2.5 centimeters long looking at the ruler, but I'm forced to estimate the last digit of the number. Why? Because we are never done with our measurement until we've estimated the last digit. I'm required to estimate the length to be something like 2.54 centimeters. Now, you might say the measured length should be 2.52 or 2.55 centimeters, and frankly, your estimate would be as correct as mine. The point is, we have to estimate the last digit, and each person will estimate differently maybe. But measuring and saying the inchworm is 2.5 centimeters long would be wrong, because we can obviously see using this ruler that it's longer than 2.5 centimeters. We are compelled to estimate the hundredths digit using this particular ruler to get closer to truth. In this next example, we will measure the volume of a liquid utilizing a graduated cylinder which measures volume in the units of milliliters. Typically, liquids will form a hyperbolic shape within the glass column called a meniscus. This effect is due to the surface tension of the liquid with the glass walls of the cylinder. We make the measurement looking at the bottom of the meniscus when reading the volume. Looking at the cylinder, we are sure the volume is at least 12 milliliters, but we know we're not done. I haven't had to estimate a number yet. The value is somewhere between 12 and 13 milliliters, so I estimate the volume to be 12.4 milliliters, though you might see it differently. You would estimate it to be 12.5 or 12.3 milliliters. Remember, though, you have to estimate and record that last digit. Our last example deals with a digital instrument such as the digital bathroom scale shown. It simply displays a number that we read. Even so, we still assume that the last value read is being estimated by the machine. In the example, the weight shown is 135.2 pounds, but we must assume that the last digit, the 0.2 pounds, is an estimated value. As we've already stated, the final measurement is not complete until we have quantified the precision or uncertainty of the final digit or number. This is where the power of making multiple measurements comes in, and the use of probability and statistics. Taking one shot at the flag in golf is probably not going to result in a perfect idea of where the flag is, though that once-in-a-lifetime hole-in-one can occur. It's better to take several readings of the sample, or take multiple samples and produce a statistical average and a standard deviation of the measurements. For example, if I want to know how much the average adult emperor penguin weighs, I would weigh as many penguins as I had or had time to weigh. Then I would report an average and standard deviation. In case you forgot, the basic equation for average and the standard deviation is on the slide, along with the calculated results of our penguin measurements. After all this work of measuring all these penguins on what we hope is a calibrated device, we end up with an average penguin weight of 85 plus or minus 4 pounds. This result contains a number, the value 85, range, the value 4, which we lovingly call an absolute error, and finally a unit of measurement, pounds, which tells us what we are measuring, mass, and is of an appropriate scale or size to match, well, the size of our penguins. The absolute error is a single digit that contains our precision and identifies which digit we are estimating in our measurement. In our example, we know we have a range of plus or minus 4 pounds in our readings, so we are guessing on the last digit in the ones position, the value 5 in our measurement. We are somewhat confident that truth lies somewhere between 81 and 89 pounds if we've adequately taken care of all the deterministic error. It would be silly to write 84.6 plus or minus 4 pounds using the calculated average from the previous slide and including a value in the tenths position because we're already guessing at the ones position. The 0.6 pounds at the end is overkill and worse, actually misleading. We can imply that we can measure a penguin with the apparatus more precisely than this instrument allows. That's why we rounded up to just 85 pounds, so we could accurately represent the measurement and the precision of that same measurement. Very often, we might simplify the measurement of 85 plus or minus 4 pounds and just write down 85 pounds for the average penguin mass, dropping the absolute error or range from the reported measurement. This is a critical loss of information, but the general implication of the random error remains in this reported measurement. The last digit of this measurement is still assumed to be the one that's estimated, even though in this form we don't know the exact magnitude of the absolute error. That's why it's even more of a crime to write 84.6 pounds for the measurement now, because this value would imply that the last digit 0.6 is uncertain and that the 4 in the ones place is known exactly. This is false, right, from our last slide. So don't do this. It's misleading to those who would read this piece of scientific data. Writing all the numbers down that show up on a calculator is actually never a good idea. We always have to keep in mind which digit is the one being estimated and round off to it. Now that we've established a proper value, we say that our measurement of 85 pounds has 2 significant figures or digits, where the last of these digits is recognized as the digit that's estimated in the measurement. We'll delve deeper into sig figs, short for significant figures, in another lecture. For now, it's important that we appreciate the idea behind every single digit of the measurement. All the work we've described in this 3-video mini-series on the measurement process emphasizes why we put so much value on representing a measurement or result of calculations with the correct number of significant figures. Having too few sig figs underestimates the precision of our instrument, and having too many sig figs overestimates the precision of the instrument. When doing a measurement or when you do an assigned chemistry problem, the last questions you want to ask yourself is, do I have the right number of significant digits in my answer so people have the correct impression of the precision of the measurements? And 2, did I include the proper units in my final answer so people know exactly what I was measuring in the first place? Any effort less than this on our part will surely cost because the scientists are very picky about their measurements. As you can see, Good measurements take a lot of work. Okay, that ends our struggle to find truth. And hopefully we can fully appreciate everything about that fundamental quantity called a measurement. See you later.